Okay, welcome to my first class on linear algebra. This is the actually basic topics of linear algebra. In this class, we'll discuss what is linear algebra and what is field, ring, and group. What is the vectors in Rn space, vector spaces, subspaces of vector space, spanning sets and linear independence, basis and dimensions. So first of all, what is linear algebra? To answer this question, what is linear algebra? Take a closer look at what we will study in this course, the most fundamental theme of linear algebra, and first topic covered in this topic, the theory of system of linear equations. You have probably encountered some small systems of linear equations in our previous mathematics courses. For example, suppose you travel on airplane between two cities that are take 5,000 kilometers apart. So if the trip on the way against a headwind takes 6 and 1/4 hour, and return trip the same day in the direction of the wind takes only 5 hours. Can you find the ground speed of the plane and the speed of the wind, assuming the both remain constant? So you can form, this is the original flight and this is the return flight. In original flight, the distance will be x minus y, and the return flight, the covered distance will be x plus y. So this making this and linear systems of equations, we can solve these types of problem easily, and by graphical method also we can apply here to find out the original distance of the location point. So this is the real life example of linear algebra. So in this case, what is linear algebra? From this example, we can find there are two words in linear algebra, linear plus algebra. So these two, and in this linear and algebra. Okay, so in this from this view, we can find the subject of linear algebra can be partially explained by the meaning of two terms comprising the title. Linear is a term you will appreciate better at the end of this course, and indeed attaining this appreciation could be taken as one of the primary goals of this course. However, for now, we can understand it to mean anything that is straight or flat. For example, in the xy plane, we might be accustomed to describing the straight lines. Is there any other kind as the set of solutions of an equation of the form y equals to mx plus b, where m is the slope of that straight line and b is the positive positive length which is cut from the y-axis, where the slope is m and y intercept is b are constant that together describe the line. So if we have studied multivariate calculus, then we'll have encountered planes. So living in 3 dimensions with coordinate described by x, y, z triples. They can be described as the set of solutions of the equations of the form x plus by plus cz plus d. This is actually a standard form of planes where a, b, c, d are the constants and together determine the planes. So from this example, we might describe planes as flat. Okay, look like table and table top of the table. So the lines in 3 dimension might be described as straight. Okay, from the multivariate calculus course, we'll recall that lines are set of points described by equations. So these types of equations, x equals to thrice t minus 4, y equals to minus 7t plus 2, and z equals to minus 9t, or it is the parameter that can take in any other values. So we can form the system of linear equations and can solve the problem easily. So this is the real life example of linear algebra. Okay, linear algebra. So from these topics, we can discuss now the uh, what is field, ring, and group, then vectors in Rn. First of all, what is the vectors? So in this part, we'll discuss the chapter vector spaces and what is the vectors in Rn actually. So the vectors in Rn, the ordered n tuples can be written as the sequence of n natural numbers x1, x2, dot, dot, up to xn. And Rn space, the set of all ordered n tuples. For example, if n equals to 1, then R1 space, the set of all real numbers. And R1 space can be represented geometrically by the x-axis. Similarly, if n equals to 2, then R2 space, the set of all ordered pair of real numbers, that means x1 and x2, and it is the R2 space can be represented geometrically by the xy plane. That means they are only ordered pair. So x-axis and y-axis. For n equals to 3 and R3 space, the set of all ordered triples of real numbers. That means three-dimensional space. So R3 space can be represented geometrically by XYZ space. That means three-dimensional space. Similarly, n equals to 4 for R4 space, the set of all ordered quadruples of real numbers. That means four-dimensional space. So in this way, we can find an vectors in Rn. That is, this is also called Euclidean space. So note that an tuples x1 up to xn can be viewed as a point in Rn with the xi's as the coordinates. If n tuples is like this, also can be viewed as a vector x. That means these the components will be what? X1, x2, dot, dot, xn in Rn with the xi's in the components. So for example, x1 and x2, this is the two-dimensional, and this can be represented as a x1, x2 look like a vector. This is the vector and this is the point vector. Okay. If u equals to u1 up u2 dot dot up to un and b equals to b another vectors. So two vectors in Rn. So if the equality if the vectors will be equal if and only if un equals to b1, then the first component equals to first component, second component equals to second component. In this way, the last component equals to last components. The vector addition, the sum of u and b can be written as like this: u plus b equals to u1 plus, then the first component plus first component, comma, second component plus second component, comma. In this way, last component plus last components. Similarly, scalar multiplication also can be written as cu. C is the scalar or constant and multiplied with the first vector u, then it can be written as cu equals to cu1 cu2 dot dot last term will be cu1. So note that the sum of two vectors and the scalar multiple of a vector in Rn is called the standard operation in Rn space. That means in n-dimensional Euclidean space. So difference can be written also like this: u minus b can be written as u plus and negative vectors of b. That means u on first vector minus first component minus second component, comma, second component minus second component of second vector, in this way. So zero vector also can be written as n-dimensional space like this: 0, 0, comma, up to 0. So the actually properties, this is the properties of vector addition and scalar multiplication. If u, b, and w be the vectors in Rn, then let c and d are the scalars. Then u plus b is a also vector in Rn, and this is also closer properties of for addition. And if u equals to, second property is u plus b equals to b plus u, this is the commutative property or of vector addition. Similarly, the associative property, u plus b sum plus w equals to u plus b plus w, and this is the associative property for vector addition. Similarly, for number 4 properties, u plus 0 equals to u, that means additive property, additive identity property. So 0 is the identity element for vector addition. Similarly, u minus the opposite of u equals to 0, then it is also called inverse property, additive inverse. So additive inverse property, c into u is a vector in Rn where closed under scalar multiplication. This is also an important property is number 6. Number 7, C into U plus B. Then a scalar multiplication with the addition of two vectors equals to Cu plus Cb. This is the distributive property for scalar multiplication over vector addition. Okay, and C plus D into U equals to Cu plus Du. This is the distributive property of a scalar multiplication over real number addition. Remember it. This is the properties of real number addition. Number 7 is vector addition. Remember it. So number 9 will be C into Du equals to CDU. That means associative property of multiplication. So, and 10, number 10, last property, 1 into U equals to U. This is the multiplicative identity property. That means what? There are 5 multiplication property and 5 addition property. Combinedly, these 10 properties will be exist in vector addition and scalar multiplication. So note that a vector U can be written as U1 to N in Rn space and can be learned as this is the column, this is the row vectors, and column vectors can be written as like this. So vector addition will be like this, and scalar multiplication will be like this. So U plus B can be treated as row vector, okay, and scalar multiplication also, and vector addition also can be treated as like this, column with the like a column vector, and Cu also can be written as a column vector also. So this is the actually properties of vector addition and scalar multiplication. Now we'll discuss about the algebraic structure. So in linear algebra, we have to usually use this structure. And first of all, this is the reference from this interesting book. And this structure can be classified into groups, ring and fields, module and vector space, and linear algebra. This is the vector space part for us. Just we are using an internal operation can be written as and a scalar multiplication. Group internal multiplication is represented as a star, but in no scalar multiplication. In ring and field, star and plus addition, vector addition and vector multiplication. So in scalar multiplication, no. So module vector space, only vector addition, and scalar multiplication exist. In algebra also same as yes. So this is the actually algebraic structure for. So field equals to what? Ring with identity and all elements except 0 within verses. So vector space equals to what? Module over the field. So before discussing the vector space, we have to discuss about the field, ring, and groups also. So okay, first of all, what is field? Field. Actually, a field F is the set of with two operations, addition plus or multiplication. This is the dot indicate for multiplication such that for all A, B, C belongs to F. A, B, C are the actually constants or a scalar. The following axioms are satisfied. Addition is associative. This is the associative laws of property, and there exists an additive identity 0. Addition is commutative. Commutative properties also exist here. Existing in additive inverse, this is the minus A, and multiplication is associative. So associative property for multiplication. And M2, there is exist a multiplicative identity 1, and multiplication is also commutative. That means A equals to A into B equals to B into A. There exists a multiplicative inverse A inverse. Okay, A inverse exists if A is not equal to 0. We have to remember this. And the distributive law also hold for the field. Roughly, all of the above mean that you have no notation for plus, minus, multiplication, plus, minus for multiplication, and division just as for regular real numbers. So field are a very beautiful structure. For some example, rational numbers, rational number Q, real numbers R, and complex number C. These are the examples are finite. However, this does not necessarily have to be in the case. The smallest example of field has just two elements. That means suppose z equals to 0 1 or bits. In computer we always use this 0 and 1 in binary numbers. The rules for addition and multiplication are the usual one. Save that 1 plus 1 equals to 0 in binary addition. So this is the actually example of field. We have to remember it. So now what is the rings? Actually, what is the rings? And a ring and R symbol R, vector addition and multiplication is a set R together with the two binary operations, addition and multiplication on R, satisfying the following axioms. For any elements A, B, C belongs to R, A plus B plus C equals to A plus B plus C. That means associative laws of addition and commutative laws. There exists 0 belongs to R called 0 such that A plus 0 equals to A. That means existence of an additive identity. There exists minus A belongs to R such that A plus minus A equals to 0, existence of additive inverse. The A into B into C equals to A into B into C. Then the associative laws of multiplication law exist. So this is the definition of ring. And there exists also 1 belongs to R such that 1 into A equals to A into 1 equals to A, existence of multiplicative identity. And number 7 property is also A into B plus C equals to A into B plus A into C. And B plus C into A equals to A into B plus C into A. That means distributive laws of multiplication. And axiom 1 to 4 are equivalent to saying this, the properties of ring for addition is an abelian group, and the ring R plus a dot is called a commutative ring if in addition, and A into B if in any ring A into B equals to B into A, that means commutative laws exist for all AB belongs to R or ring is called commutative ring. So this is the commutative ring, definition of commutative ring. The integers under addition and multiplication satisfying all of the axioms above, so that Z plus Z is a commutative ring. Also, a rational number plus Z and real number plus and multiplicative and a complex number with this are all commutative rings. If there is no confusion about the operations, we write only R for the rings, R plus and in multiplication symbols. Therefore, the rings above would be referred as Z integers, rational number, real number, or complex number. So, moreover, if we refer to the a ring R without explicitly defining its operation, it can be assumed that there are addition and multiplication. So, here's the examples of commutative ring. Integral domain also failed. Integral domains and field. This is the example of integral domain and field. So when the integral domain and field can be defined, one very useful property for the familiar number of system is the fact that if A equals to 0, either A equals to 0 or B equals to 0. This property allows us to cancel non-zero elements, because if A B equals to AC, then for A is not equal to 0, we can easily say that B equals to C. So however, this property does not hold for all rings. For example, the Z4, we have two, this is the floor function equals to 0. So we cannot always cancel since this equals to this. So this is the example of integral domain. So a field is a ring in which the non-zero elements from an abelian group under the multiplication. In other words, a field is a non-trivial commutative ring are satisfying the following extra axioms. For each non-zero elements A belongs to R, there exists A inverse belongs to R such that A into A inverse equals to 1. The ring Q, R, and C are all fields, but the integers do not form field, because the integer does not satisfy all the properties of rings. So proposition, every field is an integral domain, that is, it has no zero divisors. So a finite integral domain is a field. This is the actually proof for that. This left for you. You can understand the theorem easily. So another theorem, Jtan is a field if and only if n is a prime number. Okay, this is the also proof for you, and it will start it in class also. For example, is q root over 2 is an integral domain or a field. For the solution in this example, we know that irrational number q2 is a commutative ring. Let a plus b root over 2 is a non-zero element, so that at least one of a b is not zero. Hence, a minus b root over 2 is not equal to 0 because root over 2 is not in rational number. So we have easily see that 1 by a plus b root over 2 equals to this one. So this is an element of q root over 2 is the inverse of a plus b root over 2. Hence, q root over 2 is a field and an integral domain. Ideals. What will be the ideals and quotient ring? First of all, what is ideals? A non-empty subset I of a ring R is called ideal if R if of R if the following conditions are satisfied for all xy belongs to I means ideals, and small r belongs to ring R. So the difference x minus y belongs to I, and x multiplied with element of R equals to R into x equals to I. The condition 1 implies that I plus is a subgroup of ring R. In any ring R, R itself is a ideal, and zero element is an ideal also. So proposition, this is a proposition for any ideals, and AR equals to such that R belongs to R is called left ideal, called the principle of ideal generated by the generated by this. So this is an example of ideal, n equals to consisting of all integers multiples of n is the principal ideal generated by the n in Z. Okay, this is the examples of ideals. Now quotient ring, first will be the quotient ring. Quotient ring, let I be an ideal in the ring R, then the set of cosets forms ring under the operations defined by this. When I plus R1 plus I plus R2 equals to I plus R1. And this is the addition property, and this is the multiplication property. So if the ring R by I plus R by I is called, this ring R by I is called quotient ring or factor ring of ring R by ideals I. So now what is vector space? Actually, the definition of vector space, just using the properties of algebraic structure. A vector space over the field R consists of a set B along with two operations. One is addition, and other is multiplications. Subject for the vector addition, and for all BWU belongs to B. First law, closure law. Second law is also commutative law, associative laws of addition, and zero elements. That means additive identity elements, and inverse existence of inverse element. So these 5 laws for vector addition. Similarly, for the scalar multiplication, and for two elements of vector b and ab, two scalars, ab belongs to r, where r is the real number field. Okay, and field also we have learned the definition of field. Uh, first first law, closure law for multiplication, and this is the distributive law for multiplication and vector addition and scalar addition, and this is also the associative law. So identity elements, existence of identity elements, and we have to remember this. The symbol flower is always written as a vector addition, so that b plus w instead of this. And similarly, multiplication also often used for that symbols. Okay, so in the real vector space can be defined as like this. Vector addition can be written as closure law, and this is the commutative law, this is the associative law, and this is the existence of identity elements or zero elements, and this is the inverse existence of inverse elements. For multiplication we can use like this, and this is also closure law, and this is distributive law, this is the associative law and distributive law, and existence of identity elements 1, and 1 is called the multiplicative identity element for multiplication. So this 10 law, 5 laws for vector addition and 5 laws for scalar multiplication, combining these 10 laws can be defined as the vector space. So for example, the vector space in R2 space in 2-dimensional can be defined as like this. So for AB belongs to real number, AB are scalar, and XY are vectors. So with zero elements, we can prove like this. In R3 plane, the plane through the origin P equals to XYZ, such that X plus Y plus Z equals to 0 is a vector space. So this is an example of vector space, and P is also subspace. So we can prove it easily. Now, this is a vector space. Z is actually set of integers. Zn plus Z is vector space, but the integer on real number is not vector space, because it violates closure law under scalar multiplication. For example, in 4-dimensional vectors, zero vectors, b plus b vector space on real number is a vector space. So an element and one element vector space is a trivial space, also called trivial space. This is the example. For example, P3 can be written as like this. This is the P is a vector space with the vectors this I equals to k equals to 0 to n summation ak xk. And vector addition we can write like this, and similarly vector scalar multiplication also can be written as like this. So zero elements, if we take zero elements, that means the scalar 0, where 0 belongs to real number, then inverse of A can be written as like this. So Pn is isomorphic to the n plus 1 space in the Euclidean space. So this is the example of a Pn is a vector space, because this satisfies all the properties. Similarly, another example, f such that the domain is natural number and range is R of all real valued function of natural numbers is a vector space if vector addition like this and scalar multiplication and zero elements also exist, and inverse elements can be written as like this. So Fn is a vector countability infinite dimensions. Okay, infinite dimensions because it depends on natural number. So for example, Fn equals to n square plus 1, if f equals to 1 2 3 1 2 5 10 dot dot, then it can be also. So P is a vector space of countability infinite dimensions. And what is a function space? Function space of all real valued functions of real numbers is a vector space of uncountably infinite dimensions. For example, this is the differential equation, and this is a vector space with the vector addition like this. If we sum vector addition, and scalar multiplication is this. For a is the constant, scalar elements belongs to R, and zero elements also exist, inverse elements like this. Then the closure law satisfied. So this is why this is called vector space. Solution space of a system of linear homogeneous equations. Definition of mathematical structure is not unique. In any vector space B, we can write the properties like this, and this can be proved easily. All properties can be proved. Okay, it is very easy for you, just using the properties of vector addition, scalar multiplication. Now, what is the subspace? For any vector space, a subspace is a subset that itself a vector space under inherent operation. Okay, a subset of a vector space is a subspace if and only if it is closed under addition and scalar multiplication. That means in plane, and three-dimensional plane is a subspace of R3 space. It is the proof for you. Very easy proof. Another example. So 0 is a trivial subspace of NSP, Rn. And Rn is a subspace of Rn also. Both are improper subspace. All other subspaces are proper. So subspace is only defined with respect to inherent operations. So in this case, neither one with the additive properties and multiplicative properties is subspace of vector space on real number to real number. This is another example, proper subspace Pm if n less than m. Solution space. It is also in example 2.7 is also the subspace, but in this in the real number, positive real numbers is not a subspace of a real number, because -1 into b doesn't belongs to positive real number. This is why violate closure law. Okay, -1 into b does not belongs to positive real number. This is why this violate the closure law. This is the actually lemma. S is a non-empty subset of a vector space B with respect to the inherent operation. The following statement are equivalent. S is a subspace of B. S is closed under all linear combinations of pairs of space, and S is closed under arbitrary linear combinations. We'll left for you in class. So in we already known what is the vector space in Rn. This is the definition of Rn we have learned in our previous slides. This is the example of Rn, R2 space and R3 space. Also, this is also example of R3 space. Now, another definition is the two vectors will be equal like this, and we can with the vector addition and scalar multiplication. So in geometrically, we Rn space can be written like this for two-dimensional, which is closed under addition and scalar multiplication. This is the example of vector addition and scalar multiplication of any vectors. So in R2 space, geometrically can be represented like this. That means the considered two elements 4, 1 and 2, 3. You can write also like this. This is the same direction, and 2 times it is to length. So this is the negative vector, definition of negative vector, and subtraction also can be written. And we have studied about these 10 properties of vector addition and scalar multiplication. This is the geometrical interpretation of commutative law. And this is also example of vector addition and scalar multiplication. So we have started this row vectors and column vectors. Now what will be the dot product? This is the dot product, and this is the example of dot product. And this is also the properties of dot product. We can prove it easily. Okay. So this is the geometrical interpretation of norm. What is the norm? The norm or length or magnitudes of a vector u1 u1 u2 dot dot un belongs to Rn is denoted by this, defined by this. So norm is a very important part for a vector space. We can find out, this is the example of finding norm in R4 space. Okay. So the norm will be root over 35 and norm of B will be root over 26. So a unit vector is a vector whose norm is 1. We have to remember it. And if B is a non-zero vector, then the vector is a unit vector in the direction of B. So we can use the unit vector like this. And we can find out, this is the example for finding the vectors and norm of vector. This is the solution for finding unit vector and normalized vector. So this is the geometrical interpretation, and which can give the dot product of two vectors. So this is the definition of cosine of the angle theta, which subtended with the two vectors u and b. So finding using the norm, finding the cos theta. So this is the testing the orthogonality by using dot product of two vectors. This is also the example of dot product with the geometrical interpretation. So the vector addition and multiplication maintain two laws, triangular inequality and Pythagorean theorem. So this is the geometrical interpretation for this two. Now what will be the distance definition? Distance between 2 points. So now what is the vector space? You must know about the vector space, closure law, vector addition, and this is the example, commutative law, associative law, addition of zero elements, inverse elements. This is the definition. So this is the example of a vector space. We have to prove that W is a vector space. If W equals to A1, 0, 1, that means B equals to this. So this is the first axiom satisfied, and second axiom also satisfied, third axiom also satisfied, sixth axiom also satisfied. That means additive inverse also satisfied. So we can easily say that this is a vector space under addition. And also we can prove this matrix. This matrix is a vector space. Just vector first axiom satisfied, axiom 5 also satisfied, axiom C is also satisfied. In general, the set W PQRS matrix also is a vector space. So this is the function is also vector space, because we can easily say that axiom 1, axiom 2 and axiom 5, axiom C is also satisfied by this. So now what is the subspace? The plane consisting of all points A0. And this is the geometrical interpretation. Consider two vectors that lie in the plane. The sum of two vectors lies in also plane. The scalar multiple of a vector lies in the plane. So in general, a subset of a vector space may or may not be satisfied the closure law. However, any subset that closed under both of these operations satisfies all other vectors space. So definition is this subspace, and this is the example of subspace. So addition properties, scalar multiplication properties, sum and scalar product are in U. Therefore, U is a subspace in R3 space. Okay. Now This is also another example. We have to show that B is not a subspace because B is not closed under addition, and this is why we can says that easily this example is not a subspace. So we have to prove that this matrix U and B are the subspace. Vector addition and closure law satisfied, and scalar multiplication C belongs to R also satisfied. This is why W is closed under addition and scalar multiplication. This is why W is a subspace. Similarly, the Pn also in vector addition, and that is closed under addition and scalar multiplication also satisfied. This is why Pn is a subspace of the vector space. So we can say that in a summarizing, this condition is necessary but not sufficient. So W is a vector of the form and W is not a subspace. This is the example. Okay. And this exercise left for you. Now, what is the linear combination of a vectors? Now, what is the linear combination? Let B1, B2, dot, dot, Bm be a vectors in a space B. We said that B is a vector B in a linear combination of B1, B2, dot, dot, Bm if there exists a scalar C1, C2 such that B can be written as this. B equals to C1, B1, C2, B2. That means sum of all scalars with the vectors. This is the example of linear combinations. So just solving for C1, C2, C3, we said that this is the linear combination. There has a linear combination. This is also example. And this is also example for linear combination. And the vector space, this is also linear combination. After solving, we get C1 equals to 3, C2 equals to -2, C3 equals to 1. This is why the system has solutions, existence solution. This is also linear combination because we get solved. Now, what is the spanning of sets? The vectors B1, B2, Bm said to be a span of a vector space if every vector can be expressed as linear combination of these vectors. In this case, B1, B2, dot, dot, Bm is called spanning of vector. So we have to show that these three vectors in a span on R3 space. That means this can be written as in a linear combination, and we can solve for C1, C2, C3. The vectors, this spans in R3. That means the vectors can be written as a linear combination. Similarly, this also. Now, what will be this is a theorem generated. You'll start it in class. This is the proof for you, closed under addition and scalar multiplication. So this is why U is a subspace of B, and also linear combination. This is the example. And subspace of a vectors of the form C1 and C2. And we can also generalize the subspace of vectors of in the linear combination form. Okay. And this is the example. We have to show that U equals to B and U is the subset of B. And U can be represented as a linear combination. And we can solve for PQ. So we can easily show that B can be expressed as linear combination, and therefore B is a vector in U, and hence U equals to B. This is the geometrical interpretation. This is also an example for solve. This system has a unique solution, A equals to -4 and B equals to 3. Therefore, can be represented as a linear combination. Okay. Linear dependence and independence, very important concept for you. The concept of dependence and independence of vectors are very easily can be defined as this. The set of vectors B1, B2, dot, dot, Bm is a vector space. B is said to be linearly independent if there exists a scalar C1, C2, C, dot, dot, Cm, not all 0, such that this equals to 0. But all C's are not 0. then it's linearly dependent. But if all C is 0, then it can be linearly independent. They said vectors B1, Bn linearly independent if the linear combination equals sum of linear combination equals to 0 can only be satisfied when all C are 0. C1, C2 dot dot all Cm are 0. So that these are linearly dependent. So can be written as linear combination. So we can form system of linear equations and solve C1, C2, C3. So this is why it is called all C's are not equal to 0. This is why the set of vectors is linearly dependent. Similarly, this is also linearly independent because all C are 0. All constant are 0. This is why it is linearly independent. Similarly, we can solve this problem also. We can solve all x and all constant. Since all C are 0, this is why linearly independent. So this is the example, another example. And linearly dependent vectors lie on a line, but linearly independent vectors do not lie on a line. Okay, they lie on different individual line. This is the geometrical interpretation of linearly dependence and independence of B1 and B2 in R3 space, and in R2 space. But in R3 space, this is the B1, B2, B3 in linearly dependent vectors lie in the plane. Okay, B1, B2, B3 linearly independent vectors do not lie in a plane, in different plane. They lie on different plane. So this is the theorem. B is a vector space. The set of any vectors in B that contains the 0 is linearly dependent. This is the proof. And this is also example. Span. Basis and dimension. Now, what is the basis and dimension? A finite set of vectors B1, B2 dot dot Bm is called basis for a vector space B if the set spans B and is linearly independent. So a standard basis, the set of n vectors 1, 0, 0, 0, 1, 0, 0, and dot dot 0, 0, 1. That means is x-axis in y-axis and z-axis and etc. is a basis for Rn space. This basis is called a standard basis for Rn. How we can prove it? This is the example for the basis in R3. Let x1, x2 dot an arbitrary element of R3 space. Suppose this x1, x2, x3 can be written as linear combination of this. Okay, where a1, a2, a3 are scalars. Now we can solve easily. So the set spans the space. Is linearly independent. Consider the element this. The identity leads to the system of equations. We can solve it easily. All b's are 0. That means it's the unique solution. Thus, the set is linearly independent. So these three vectors spans R3 and is linearly independent. It forms the basis for R3. So another example for linearly independent and spans. So Px can be written as the linear combination of A1, A2, A3, and it gives the solution. Thus, the polynomial P can be expressed as the function fg is span P2. They form a basis for P2. Now, this is the actually theorem, and we can prove it easily. The let B1, B2 to Bn be a basis for the vector space B. If W1, W2, Wm is a set of more than n vectors in B, then the set is linearly dependent. So it's very easy theorem for you, just using linear combinations properties. If m is greater than n, there are many solutions in the system. This is why linearly dependent. This is also an important theorem for you. Any two bases for vector space B consist of the same number of vectors. Now, what is the dimension? If the vector B has a basis consist of n vectors, then the dimension of B is said to be n, and write as d B for the dimension of B. B is finite dimensional if such a finite basis exists, and B is infinite dimensional otherwise. Okay, so for example, the dimension, finding the dimension, consider these two vectors in R3 space. These vectors are generated subspace of B R3 consisting of the vectors of the form linear combination. So the vectors span this subspace. So this is the basis. These two vectors are basis for B. So dimension will be 2. Now the theorem, the origin is subspace R3. The dimension of this subspace is defined to be 0. A one-dimensional subspace of R3 are lines through the origin, and two-dimensional subspace of R3 are plane through the origin. This is the actually geometrical interpretation for you, and this is the proof of this theorem. So another theorem, you can very important theorem for a dimension. Prove that this is the basis for R3. The dimension will be R3. It satisfies, it's sufficient to show that the set is linearly independent or it spans R3. Linearly independence. So we can easily find the C1, C2, C3, all C's are 0. This is why vectors are linearly independent. So the set are basis in R3 space. This is the also example can be solved for you. So this is the actually basic concept of vector space.